Okay. Let's take a look at the data acquisition exercise. And by the way, the deadline for this exercise is also 2 weeks. Okay. So let's see. So basically, first part is to make a. Let's see, what does it say? An edit. Yeah, there's an ADC. First part is basically just to test that we can read anything from the A2D converter. Okay. And display it to LCD. And then there's actually a variable resistor here on the corner. Here, VR signal is something between 0 and 5 volts, depending on the this potentiometer here. Turn wheel, and this is just to get a reading. On part 2, I think I have a yes. There is actually a real signal from well, quite low precision, but anyways, an analog the temperature sensor on a single chip. 15 years ago, this was a big thing. To have a voltage proportional to current temperature. Currently, basically, these are kind of obsolete technology. On a similar chip, you can have all the intelligence you need and with higher precision and digital output. But anyways, for this one, this is just a good example of a sensor. So actually, before going to that in detail, let me open the datasheet of that sensor. We used to actually buy these something like 80 pieces a year, because this is very sensitive on how you connect it. And if you connect the power to wrong pin, you will definitely destroy the chip. But those are cheap. But anyways, just a reminder. So read the data sheet, take a look at the last pages. Oh, well, that was actually on the first page. The pin out. Okay. The positive power and the ground are on the opposite corners. But of course, then what does it say here? This is a bottom view. Okay, you need to take care of that you really have this on these corners. If you switch those, then you will come to speak to me. May I have another one? Okay, now you have been warned. So, but anyway, so this device gives somewhat calibrated the analog signal, which is proportional to the temperature, and the conversion is basically quite simple. It's 0 millivolts plus 10 millivolts for each centigrade. Here we have something like 23, 24 Celsius degrees, which means you should be getting something like 240 milliwatt signal for. And then the exercise is actually, did I mark it here? Yes, displays the ADC value, that's a digital value, and corresponding temperature on the first row of the LCD. Okay. So you need to do also this is your first thermometer. It's a crappy one, but you did it yourself, right? Okay. Yes. Okay, that's actually a kind of indexing. If this was going to some table or something, you would like to have a running index on the big. Yeah, so it's just a row index. So incrementing every time you take a sample, it gives the sample number. Okay. Good. So that's what this exercise is all about. And then, okay, another couple of things. You also need to make the signal conditioning circuit, and then actually I will help you, and we can do this low pass filter together. Characterize that one. Okay, and then this actually that we are having oversampled system, digital system, around 100 samples per second. But of course, well, temperature is kind of slow, and that means that basically you are downsampling that one. So if you remember our slide, so let's see, is that the one about signal conditioning? Oops, signal conditioning. Where did I have signal conditioning? I had added somewhere. Sorry, I draw it there. The signal conditioning. Maybe I should actually draw it back. Okay. So this exercise is about having that temperature measuring device, and then inside of PSOC you have the analog low pass filtering. Okay, actually it starts okay, right there. Start with some multiplexing of the signals to put it on the right place, and then we would have this low pass filter, probably with the gain. Well, at the end of the day, you are you would like to have as precise as possible values, and now our nominal level of signal is 240 millivolts. If you have gain of 10, that would be 2.4 millivolts. So you basically match the sensor signal better to your A to D conversion then. Okay, I'll just this is question mark gain. Okay, then you have the A to D converter with high sampling rate. Okay, then you would have some digital signal processing, which basically means that you do the downsampling. So downsampling is usually marked like that. So downsampling at, was it once a second or something like that? And here the FS2 is around 1 samples per second. And that data actually is then, you have the conversion here. So post-processing basically means that you have the LCD output, or raw data, from A to D, or actually the raw data after downsampling, and then you have the temperature at the degrees of Celsius and the running index. Those would be on LCD. Okay. So that part is the exercise. Good. So, yeah, so system calculates time average data with downsampling rate of 2 samples per second. Okay, so basically this wasn't 1, this is 2. Twice a second it updates the LCD about this rate. Ding, 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 ding. Okay, couple of hints there. So this here requires some sort of interrupt, and basically you need to calculate the summing the running sum of the values. Okay, I think it goes something like this. Between those 500 milliseconds. So summing all of those values, and then also the running index. So how many samples you have summed there. And then divide the sum by that number. So running average. So actually this is boxcar averaging. So you should wait for a while and sum everything, and then at the end you will divide it by the number. Okay, and okay, therefore this does not need to be exactly 100 samples per second. There are some easy A to D converters on this PSOC system that give automatically if you leave it running freely, then it gives automatically some sampling rate there, a sampling rate. But here, this is the most important to have this one quite exact. Fortunately, you can do it with the sleep timer. So twice a second, you wake up and read what was the sum and the how many values were sampled. As long as actually somehow you have the knowledge about when the conversion is ready. Okay. Yeah, so this could be actually the sleep timer. This requires some sort of other interrupt. And then a couple of hints there too. But let me open the PSOC designer and I'll start going through the parts what you would be needing for this exercise. And just for fun, I will start everything from scratch. So new project, chip level, that's fine. And the name of this project would be something like TKP sensors exercise 2 N-source. What is N-source? Sensors. And then, as earlier, check that your device is that CY8C27443 PXI. If not, select it. Okay. So today we need LCD. That was under miscellaneous digital. LCD module, and I'll just call it LCD. That would be on port 2. Okay, good. That's fine. Then we need also A to D converter. But for this part, data, the signal conditioning, we need also the analog filter. That's under the filters. There are basically different choices. There are 6 different choices. BPF is band pass filter. We don't need the band pass. We need low pass, which are the lowest 2, or actually 4 the lowest. ELPF is a little bit different from the LPF. I think the E was, well, let's see. What does it say? 2-pole elliptical low pass filter. Okay, it's just another one type of filter. Elliptical filter is nearly let's see, linear phase shift filter, meaning the group delay is constant. And that would be used for basically telecom kind of systems. Like if you had a noisy line for dual tone multiple frequency, then you would get rid of the noise with that filter. But I don't think that there are too many places to have it. But then we have this LPF2 and LPF4, so either 2-pole or 4-pole filter. The difference is basically that on 2-pole you get this, is it 20 decibels? Oh, 12. Yes, 20 decibels per decade transition band, but on 4-pole you get 40 dB per the attenuation. So it's steeper. For this purpose, we can actually use the LPF2, 2-pole low pass filter, and even there you need more choices. Basically, this defines what blocks are used by the filter and which blocks then you have free for other analog systems. And currently we have only the we need only the gain block, so we can actually use the lower blocks, the switch capacitor blocks for this filter, I think. Okay, so that one actually pairs of filter to form pole use internal chip connection. Okay, but well, just for fun, I will just select the second one. So these are just different configurations, and depending on how many and in which blocks are required for other analog functions, then that one defines which blocks you would, which configuration you use. Practically, this will give the same the function. So properties are about the same. Yep. That's fine. Okay. And now we have actually reserved those blocks, which are now blue. Good. Good. So next, we might actually also need to have this one. I don't know. or we can actually just route it permanently to that pin using those things. Then we might actually need to have the gain on the other side. If you need a gain block, it's a good idea to put it as a first. Two good reasons. Then you have the least of this noise on the input, and when you amplify it, you are not amplifying the internal noise of the system. Okay. So let me actually change the order here. Another good reason is that usually you can combine, or it also makes the routing of the signal to this filtering block usually easier that way. Okay. So let me just add there this gain, which is the amplifier, and just PGA, which is simply programmable gain amplifier. By the way, the other amplifiers there are, it's inverting amplifier. Okay, no much use usually. Well, in some cases you might want to have the opposite or the negative gain. Then basically there are two comparators, 1-bit conversion. So these are A to D converters, 1-bit A to D converters. Low power or the just ordinary comparator. Low power is slower than this ordinary. Then there's also some sort of instrumentation amplifier, as I told you about. If you have a noisy environment and you have a bipolar signal, or actually this not single but dual-ended signals, so differential signals.
You cancel the noise.
Yes, common mode noise. All right, but we are using the PGA here since our signal will be on this board, no long wires. All right, so PGA, programmable gain amplifier. We can later on move those, but just for fun, we can start by setting some values. For example, for the PGA gain, I start with gain 1. And as you can see there, you can select different gains, basically, but only those values, because it's digitally controlled. There are only some preset values that you can select, but there are enough of these. So basically, it starts from like an attenuator, and then ends up at 48 gain. And this is not decibels. This is just linear gain. Okay, is there number 10? No, there's no number 10. You don't probably need it. You should use 8 or something like that. Okay, input. It will be from output, and let's see, for example, analog column input multiplexer 0. And in my exercise, let's see, where does the, okay, use port 0.0 for your analog signal. Can this multiplexer? No, this multiplexer cannot actually handle 0.0. So we actually have to move this gain block to another block. Okay. This can be then selected to this column, the input select, which can be then connected to port 00. So routing of the signal from here, to the gain block. Okay. Now we need to be a little bit careful. The reference for this gain means that, this gain actually is gain compared to the reference level, meaning that basically output is G times input voltage minus reference voltage. Our signal is between 0 to whatever to say, around maybe 1 volt or something like that. It's unipolar, which actually tells to this that if we want to have this, the result easily to be interpreted, we better use also unipolar gain here. There are differences between those different references. So we actually, analog ground would be at the middle of the voltage range. Okay. So we actually use VSS, which is the real ground. Same reference as your signal. So for single-ended signals, the reference for the gain should be the same. Yes, you have a question.
The pressure sensor, are we going to put which voltage running on it? Which voltage is going to be running on the pressure sensor?
Yeah, what is available. Okay, so this, I think the range is somewhere. That's actually a good, excellent question, since you always should. I think this is something like that, from 4 to 20 volts, the power for that. And we have two choices in this PSOC, either 3.3 volts or 5 volts. And for this one, of course, then it's 5, practically. 5 volts.
If we're using 5 volts, we shouldn't use like a voltage divider, like a resistance going to the pressure sensor. We shouldn't use like a resistance after the temperature sensor.
No. No, it's just power to the temperature sensor. Power to the temperature sensor, V plus, and then V out is our signal. And that signal is 10 millivolts plus 10 millivolts per degrees of Celsius, as it says on the reference, or the data sheet. Okay, so now we have the amplifier and signal into it. Reference, the same reference as for the signal. Then, well, analog bus. If we want to, for some reason, take the signal out of the chip. Actually, I have used this chip to provide 3 amplifiers. 3 programmable gain amplifiers and nothing else, only that. It can be done. Okay, but otherwise, usually all the signals are inside. Okay, so now disable analog bus. If I enable it, actually it goes to this analog bus, and then you can turn it to only to port 0.5, nowhere else. But we don't need the output signal. Okay, unless you want to basically have a multimeter and check if your amplifier works as you think it works. Okay, so we have some parts done. Let's see, yes. Then let's see, let me make sure that this is on. Okay, so amplifier, and then we have low pass filter. Next part, how to route the amplifier signal to our low pass filter. Let's go and try to figure it out. I want to do this one now. I can select only those 4. Analog ASD11, ASD20 and ASD22 can be input for that one. That's not a good news, since the program gain amplifier makes sense only on these blocks. Well, let's try another place for the I didn't do anything. Now we wait. So practically you need to find a block where you can route the signal. This doesn't look good. Let me unplace that one and yeah. Let's remove it and put it there again. That was LPF2 and that was the second one, okay. And no, not that one, but then what? Doesn't do much here. Delete. Do I have to use some other? Well, let me try the first configuration. Does it? Okay. Yeah. So it was about the configuration where it can be fixed. All right, let's see if we have better luck with this configuration. And there we basically, let's see. Input can be from ASB01. Wonderful. So now I have PGA signal connected to my filter. All right. Then some things like polarity. Default is inverting because it's easier on the devices. But actually we do not want inverting output. We want a just this normal output, so to speak. All right. Then we actually need to fix these capacitors. Whoa, how do I do that one? Actually, fortunately, there is a low-pass filter wizard that helps you designing the filter. And this is more or less quite nice and graphical interface. And basically, what we need to define here is the corner frequency for this filter, and also the sample rate for this filter. This is switched capacitor filter. Okay, meaning that on the Allen key structure of the filter, all the resistors are replaced by variable resistors implemented on switched capacitor technology. Okay. Right. So our target corner frequency is 10 Hertz, meaning Hertz. But now we need to also tweak that sample frequency. So this would be possible to do with this block. So corner frequency 10 Hertz, sample frequency 1200 would look quite nice. So see, this blue one is say theoretical on continuous time Sallen-Keyes filter, but due to the switch capacitor technology you actually have that orange, meaning that basically this filter also, since a switch capacitor, so basically it's a sampling system, and with the sampling you have the aliasing, and this filter aliasing starts at 600 Hertz, half of the sample rate right there. Makes kind of sort of sense in a weird way. Alrighty, let's see, let me try to tweak this a little bit more. Well, it doesn't, it's not getting any better or worse like that. But anyways, the corner frequency 10, the sample frequency should be in range of about 100 times faster than the corner frequency. That's a rule of thumb. Between 50 times to 200 times. Tweaking is allowed. All right, filter type. Okay, filter type. You should actually take a look at some signal processing book, how these actually differ. But these are classical filters. Butterworth meaning flat passband. Chebyshev meaning a constant ripple on passband. Bessel means almost linear the phase shift, and then there's those custom complex poles with complex poles or real poles. Well, those are just custom. You can customize it yourself, meaning you can actually make a high Q filter using also this one, which would be bandpass filter practically. Anyways, so Butterworth is just as good as any. Although let's see, 1 decibel Chebyshev actually have a little bit better stop band attenuation. Very little. Okay. If you need better than this, you either go to the 4-pole, this is 2-pole system, which means 2 more blocks used, or go to analog. Analog filter would be better choice, but then you have fixed also the corner frequency. All right, so a couple of things we need to take a look at this. First of all, you can actually have a gain on this filter block too. Since a switch capacitor, you can practically have quite good control on how many dB gain you have. Within, well, I think when 1 decibel is a little bit optimistic for this one, but at least 1 decibel level, you can have this gain, the control. Okay, this you should make a note of. So, column clock rate, 4000 Hertz. Okay, so it's 4000 Hertz clock rate. Switch capacitor system always needs that the switching clock, and now we have that not 4 kilohertz signal that we are now still missing. We have just a place here. Which is the input modulator clock. You can select the modulator clock from 8 different sources. Or is it 7? Yeah, actually 7 different sources. And you must select it. So somehow you need to get 4 kilohertz clock from the system clock rate, which is 24 megahertz. So in between you need a divider of, how much is that one? Divided by 6000, right? I leave that one to you how to make it. I'll just show you some points how to get that. Divider for system clock. Good. So, some places where you can find this division, you cannot, can you? Actually, 6000 is how many bytes you need for that one. I think you can get quite close even with those dividers. Can you? So the basically can get from the system clock. If you use VC1, 2 and 3 in cascade, you get 16 times 16 times 256 is the highest. Okay, so well, yeah, yes you can. So the highest divider is 65,000 and so on, yeah.
We should use double of that because some have to be double frequencies. So instead of 6000 should be like 3000?
What did it say on the okay, LPF wizard? That gives column clock 4000. Column clock. Oh, it gives you the divider here. Okay, divide by n. 6000. That's nice. Okay, so divider is 6000 from the system clock. So you need to have that signal. Okay, and then you get 10 hertz the corner frequency. Okay. Whoa! What happened? Ooh, it came back. I was worried a little bit. So let me save everything just for fun. Yes, you have a question?
Can I input the blocks VC1, 2, or 3 into the bus filter? Because I'm not sure with the modulated clock which.
Right. Let's see. Can you actually? Yeah, that's good. Modulator clock. Oh, you cannot even use that one. So you need to actually take it from somewhere. Yeah, right. So you can actually have it on row 0 broadcast. Row 0 broadcast signal is here. Or global out even. You can use these. Okay. So basically we need to route it through those in any case, unless, yeah, correct. Modulator clock has to be taken from some of those blocks. Okay, let's do that. So it means that we need to have a divider block here, and dividers are actually same as timers. 8 bits will do just fine, and you can actually then configure this timer such that it gives a decent clock to that system. For example, well, this, if this can take the modulator can be connected to global out even 0. So it's now here. it means that we need to actually have the for example, compare out on row 0 and that one connected to output even 0. Okay. I believe that now I have the clock coming from, wait a minute. Let's take a closer look actually on the data sheet. I'm not sure about this, where actually that clock should be connected, since there's also this column clock that goes into each of these circuits. Ah, yeah. Okay, okay. Let's take that one back. It's not the modulator that we actually need to fix, but we need to fix this analog column clock. That's where the signal, the clock signal comes from this block. Alright, and this can be taken either from VC1 or VC2, and well, that's not enough. There's no selection of VC3. So we actually have to get it from analog clock select 0. Okay, and then that can be connected to those digital blocks. Whoa. So yeah, it's a little bit, well, it's not complicated, it's just fuzzy. Not even complicated, it's fuzzy how the connection should be done. Oh, well, everything is on data sheets, but well, I'm lazy. All right, so basically the data sheet is telling that the clocks are actually modulated clocks. Well, it's modulated clocks. Let's see. Power settings, placement, parameters, parameters. The polarity, the function available only on topologies. It's not available. We can just select 0, the none on this one. Okay. So there it is. The user is expected to initiate a PWM or a counter at 4 times the sampler frequency or use either VC1 or VC2 clocks. So sample frequency was 1000. Was it 1000? No. It wasn't 1000. Was it? Then this one tells that the PWM or timer should be running at 4000 hertz, not 6000. No, 4000 hertz. Yeah. Yeah, I'm confused. Yeah. Yes. 4000 hertz. What?
We can select the system clock so it does not have to be 24 megahertz.
Yeah, well, system clock is always 24 or external crystal. Yeah, the CPU clock can run in lower speed, but the system clock is 24. Yeah. Okay, so now basically we just need to have this timer running at 4000 hertz.
So if I select non-modulated clock for the filter block, it automatically listens to the clock input we selected. If we select non-modulated clock for the...
Yes, modulator. Yeah. For low pass filter, this modulator clock is none.
Okay, then it listens to the clock input.
Yeah. Yes. Okay, so that timer should be actually 4000 hertz. I will rename it timer 4000. And then one way to get it, okay, is to divide by 10 and 10. Then you basically have just 60 on this one. Period is 59. Compare value, okay. I took the compare out, or that was just the output. Compare value could be 1. It's 0, sorry. So this timer block actually is exactly the same as a PWM clock. It has both functions. So compare value is the PWM output, actually comes from the compare value. So it compares this value to the current count. And otherwise a counter actually runs from 0 until it hits this period, and then starts over. Yeah. Okay, 59 means that it starts from 0. The last one is 59. So this is now divided by 60. Compare type, well, anything will do here, because basically this is not using the PWM output. Interrupt type, we don't need to make this one interrupt. It's not a good idea to have 6,000 interrupts a second. So no. Clock sync, always, okay, read the manual, but basically most of the time you actually use sync to sys clock, and those are just fine. Now we just need to take the correct input for this clock. So VC2, since I had VC1 is a system clock divided by that one, that's now 2.4 megahertz. Then we have, did I get it correct? 60, and that's 60. Well, yeah. 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 Okay, bingo. Yeah, 10 times 10 times 60. Yeah, 24 megahertz is divided by 10, and that one is then divided by another 10, and then we divide again by 60. Then we have divider is 6,000. That was the last confusion. Yeah, sure. All right, timer gain. We have the low pass filter. We have LCD. What else do you need? Yeah, A to D converter would be nice. That I will just show you, since basically we have plenty of different type of A to D conversions. One is A to D conversion incremental, which is quite close to the integrating, but it's single slope integrating, and that's not accurate nor the high resolution. Another incremental with some variability. I have no idea what this is. But anyways, then there are delta sigmas, and basically this kind of cheap devices, delta sigmas are better than the other forms usually. And they are basically dual 8-bit, dual A to D converter of something, probably the same the technology or the same type but different different kind of the modules there. My favorite is easy A to D. Well, there you can actually select the how many bits you want, and it gives you how fast it is. Yeah, the resolution, 8 bits or 11 bits. These devices have accuracy of 0.5 degrees, and the whole range is about few degrees. So I don't think that the you need many bits. So 8-bit is just fine for this exercise. Otherwise, you need always to check the application, how accurate you want to be. That gives you exactly how many bits at least you need to have, then you add some. Okay, just for fun, there's also successive approximation register type, but only at 6 bits. That basically comes from the fact how many blocks there are and the physical properties. Okay, so delta sigma. Let me take a quick look at the delta sigma. What does it look like? Does it gives in bed? What's the noise and the number of PC so blocks? First order modulator or second order modulator? Maybe I should actually take a look at the data sheet. My concern on these actually different since the different A to D converters is that I would like to have a block that gives me interrupt. So when the converter is ready, it interrupts that I can go and do the decimation. This looks like it's giving CPU interrupt. Good. How about the easy? Does it give me also in or conversion into? Yes, this one actually also can give interrupt. All right. Good. Let's take my favorite. Single state is as good as any. Let's see where this go. Yep, that's a good place. I don't care. As long as I can actually select the signal from my filter to go to the A to D converter. And maybe I can actually do it. That's the first place to check on this. So input comes currently from ACB 01. No good. No good. How's that? ACB 03. No good. Analog ASC 12. AC 13. Okay, it looks like I had to do some work on here. So maybe change it to another block and see if we have any ACB 02, SD 13 and 12. Okay, maybe I can. There are a couple of ways to do it. You can reroute this signal back to input by using the analog buffer, but well, yes, you can actually. 03 could be rerouted, and then we can use this multiplexer actually. Well, these two multiplexers to get it back. That's fine. Another way, actually, let's see, input ACB 02, now it's there. We can actually probably put a programmable gain amplifier again and route this signal to here. The this SOC circuits or this SOC device is actually really nice since you can do things inside of them, but it has, as I told you on the first lecture, there are some limitations on how you route the signal. So those considerations you just need to live with. Okay, well, let's see if we can actually do this one by adding another amplifier, not here but there. Okay, now we have a PGA. The another one, PGA ADC here, and input from ASD30. No, it doesn't help us. Well, it looks like we have to actually use the analog bus. Analog bus output buffer 0 and route this signal to port 03 and then reroute that signal to 03. It goes through pin. So the low pass filter output to analog bus. So this low pass filter output will be on analog output bus 0. We turned the this buffer on, which actually connects this one to port 03. So now our low pass filter data is actually going to a pin, which cannot be used to anything else. Okay, and then this one is then taking as a signal to this PGA in here using the analog column max input 2. And well, we need to have the gain, just gain 1 here, and that's it. Another way would have been to select some other A to D converter and try if we can directly locate the A to D converter, for example, below this the PGA gain block next to that the low pass filter, then there would have been a connection possibility from those blocks to the next one. But well, it's always a compromise. There's plenty of different configurations you can try. But now it's done. A to D, PGA, another PGA for connecting the signal, low pass filter. Then we have the timer for the low pass filter clock.
It seems now that the low pass filter clock comes from the ADC. The timer block is not connected to the low pass filter clock.
Timer block. Oh, yeah, you're right. What the heck is happening here? Oh, okay, I see. Ah, yeah, because the easy A to DC, yeah. So we broke this system. Now we need to actually have some other way to connect that one, which means, well, we have the another. Okay, there's also analog clock 1 select. Analog clock 0 select is now for the easy A to D. And now analog clock 1 select is still available, and that can be connected to DB there. Okay. Got it? The problem with those wizard and easy kind of things that they are, it seems that they are overriding your own design. Okay. And we still have some free blocks. Let's fill those too. Not really seriously. Okay. And let's see, yeah, the easy A to D converter should be make to interrupt. I don't see the interrupt kind of things here. Well, but maybe it's, yeah. But anyways, the resolution, we don't need that much resolution. Maybe 8-bit would be enough. Then the sample rate for this block. So basically, now it should be more than 100 hertz, or around 100 hertz. Well, 390 is quite a lot. So if we make 10 bits converter, then actually it can run at 114 samples per second. So these are as kilo samples per second. Okay. Buffer gain, reference, VSS fine, analog ground disable, outputs disable, offset compensation frequency, don't touch that. Okay. Data format unsigned, yes. Okay, now the question is, where is our reference level? This is A to D converter, which always have some voltage reference somewhere. The question is, where is the voltage reference right now? There's no setting for it other than global. There, reference multiplexer. That setting defines on what is the input range for the A to D converter. So if you want your full input from 0 to VCC, then the reference multiplexer should be set to VDD over 2 plus minus VDD to over 2. But then if your voltage power actually fluctuates, then it affects directly on your measurements. So never use that one. Band cap is good, since the band cap in this circuit, I think it was 1.3 volts band cap reference, which is more or less constant. I wouldn't count on it how constant it is, but anyways, it's better than that fluctuating 5 volts. So basically that gives us about 2.6 volts range. For 5 volt systems, you can have, let's see, you can almost have the 2 times band gap. 1.6 times band gap is quite good setting for anything. So it's roughly at 4 volts, the full range. So it's the analog reference now. Analog reference ground is now at 2 volts. Okay. So this analog ground, what it refers, it's at the middle of this setting. All right, so that's global resources 1.6 times band gap plus minus 1.6 times band gap. And that's roughly 2 volts plus minus 2 volts. But it's rather constant. And then you can actually calibrate it. Ah. All right, good. Those settings. Anything missing here? Oh yeah, the timer. We have a timer, but do we need a timer interrupt for interrupting at 2? Well, hopefully not. Okay. So next, generate configuration files. It had some warnings. What did it warn me about? See output window.
values have not been initialized.
Oh, uninitialized values is on A to D converter. That's initialized. PGA gain. Oh, okay. Does it have no? Yep, that was unreferenced. And so analog bus disable. Disable. How about this one? Disable. That should be okay. Okay. Timer. Oh, okay, okay. These are capture. I think it was low. Terminal count none. Interrupt top type. Well, capture. All right. On timer, you should actually take a look at the data sheet to make sure that all these parameters are set up correctly. Let's see. It says something about capture. The software capture mechanism will not operate correctly if this parameter is set to value of 1 or is held high externally. So it means that actually capture, if you are not using capture signal, then basically you should set it low internally. All right. Okay. Maybe that one was enough to, and then we can click again the generate. One warning still. There's still some parameter missing. Okay. I don't worry about that one. All right. But anyways, now we have that piece of thing defined on the system. In principle, only thing required now is the code, and the code on main.c, which means first you need to start all the modules. Oh, sleep timer is missing. You know where to find it. Then you have the forever loop. Forever loop, and in between you will do what? You sleep for half second and then do the displays, or calculate and display, right? Or well, calculate this average and remember also to when you take those values, hopefully we can get this loop running automatically by that interrupt service, and we just need to find where to patch a little bit of the of our code, find a place where you can actually put your own interrupt service routine that runs automatically. Okay, and basically when you take those values which are automatically calculated, or sum is increasing, also the number of values on the sum is increasing. When you take those values, then you probably want to then refresh those back to the 0, right? Basically you start by fetching then calculate average, then calculate temperature in Celsius, Then here you will have the show them on LCD, and then sleep 500 milliseconds. The sleep timer itself makes sure that it takes into account also the time you are spending on the on calculations and that other stuff. Yes, you have a question.
The idea of the average is that I just take the sum of every ACD result I have since we
Yes.
started running and
Mhm.
simply by the number of ADC conversions I already.
Yes, yes.
So not that complicated as
No. It's just it's a sum up, and then once in a while I'll go and divide. And
every ADC conversion I do the position gets.
Mhm, yeah. And actually, before fetching those numbers, it's a good idea to stop ADC, or at least stop touching those numbers. So you are not taking samples in during this when you are fetching the values. Otherwise, you will get an interrupt at the middle of, in between of reading the sum and the values. It can happen. So this would be the safe way. Stops the service messing the those global variables, fetch the values, and then actually null them, the global values, null them, so you will use temporary variables to fetch them, and then null the original, start the A to D again. Then it can run there, already starting the summing up again, and basically while you are doing the calculations here, or basically the calculations here doesn't take too long. But then when you are starting to put those on the LCD, that takes time. That's quite slow device. And while you are still updating, although the function is still updating LCD, you don't want to miss all of those, half of the data what is coming there. Okay. So, in principle, that's more or less everything what you need to do. Let's take a look at the interrupt. I want to see the interrupt, so I will just add here the interrupt service routine to handle the ADC data after each conversion. Let's where is easy A to D conversion, and there we have the application programming interface, start, stop, set buffer gain. What else we have? Get samples. We can check if the conversion is available. We can read the data and clear the data flag, set reference, but where do we have the it's not too obvious where to patch your interrupt service code. We need to take a look at the library files. Especially there's that easy A to D converter int.asm. So that actually has currently whatever is there for that routine, and you can actually modify those with some precautions. Let's see. Alrighty. runs at the end. Check for overflow. Does it have any custom code? Compensation ready. Offset compensation ready. What? Conversion ready. Oh shit. It doesn't have the no, sample data is now in iResult. Okay. So here we have the conversion is ready. So what we can do now is to call our own routine with some caution about, okay, this interrupt service routine has already preserved the values of the A register. If you need to use the X register, you must preserve its value and restore. We don't know that. But if we use a normal call or long call to jump into your own routine, it should be safe. Should be. I don't know. We'll see. And how to patch that one. It's quite simple. Above this banner, so whatever I put here, it's my code, and basically it will be compiled. So I can put here long call to my C routine. Okay, if you put here underscore, then you can actually put your own function call here. For example, if you have the cma.c here, if your function is like void my ISR, okay, void, let's put it, make it void. You can now do whatever you please. So we can then refer to iResult by making a small prototype of it and then refer it here somehow. Or do I need to actually? No, okay. I can refer it the easiest way by making here a global variable, integer, or should be external integer, yes, integer, and that would be ADC result. Hey, wait a minute, I don't need to do that. I just know that the conversion is now ready. Okay, I can actually here use the all right, let's see, integer current value, and then I have here, okay, the integer sum starting from 0, and then I have integer numbers starting from 0, okay, integer cval, and cval equals, there you can actually read the current ADC value, since the conversion is ready, right? We don't need to check it, hopefully. And then basically what you need to do is sum plus equals cval and num plus plus. And if your function is called myISR, then it will be referred here as my the underscore my ISR. That's the bits and pieces you need to do here.
Okay, so that just simply calls my ISR when the
Yes, yes. When it reaches here, it's doing your calls your routine, and then after your routine it comes back.
and my assembler knowledge is kind of not that great.
Yeah, you don't need that's the only line you need ever. Ei se oo täällä. Kimmo. Ei seisy pöydän alla. Okay, so yeah, so that's the only assembly code you need, and then you just need to find the place to tweak it. If you need to access any interrupt service routine, then there's a corresponding the module int.asm file, and always inside of those files there are some places you can basically tweak your own code in. And this is the perfect place, since it says, okay, sample data is now in iResult, meaning, okay, if I call a corresponding routine which reads that iResult, excellent. I don't need to check if the conversion is ready, since I know it already. Okay. On that point, it calls my routine in here, which basically just first the whatever read the current A to D value into a just a buffer value, and then updates the sum and how many values there are on the sum. Good. So as soon as the A to D conversion converter is running, this starts updating the sum and the num. One warning. This running sum is really great, but you need to make sure that you are not doing accidentally here overflow. We are summing about 50 samples here. Okay, 50. That's let's see how many bits you need for 50. 64 is 2 to the power of 6, right? Maybe. Yeah, 2 to the power of 6. You need 6 bits for the sum, in addition to your A to D conversion bits. Our A to D converter is now 10 bits. Plus 6. 16 bits. These are integers. Do you see a problem? Yeah, it might actually end up being overflow, since this is signed integers. Except in this case, our values are actually unsigned integers, since we click the unsigned that parameter on this module. So it might be a good, but on the other hand, the software is cheap, so we could have the sum as long integer. This will be fine. Okay. I will let you to fill the empty block spaces here. Okay, and we have 2 weeks of the time to do it, and I have these LM35 type of analog sensors here for our if in Frankfurt there are no LM35s, then you can actually do it with the just with this variable resistor here. But I think Michalik has some LM35s on stock, or some other analog sensor. Any sensor would do. So the sensor here, it's just for to have something tangible instead of just, you know, see, I can make the values go higher and lower. Okay, good. Any questions? Yes.
Basically, this time we submit 2 projects, as you say, and task 2 that we should clone the first project.
Well, you return only the 2B. Yeah.
So,
Yep, yep. Yeah, just the final version, which has the we're using this one, and I can test it on my device. Mm. I know. You're really a prototype of German. Really stereotype. Yeah, not prototype. Stereotype. Very stereotypic. Okay, good. So yeah, so basically you need to return only the temperature sensor part of this as a project, and the main of that one. Excellent. If no other questions, then I will just close this.